Hey guys, welcome. Yeah, so problem two here, and we have to deal with a couple of improper integrals. This is the first of them. Remember, improper integrals come with a particular grammar, which is, we can't evaluate at infinity, so we change this infinity to, say, the letter b, and then we say limit as b goes to infinity of 0 to b of this integral, yeah? All right, so with that proper grammar fix, I actually used a instead of b, which is, more natural. So I don't know why I said b, but yeah, this is what I was talking about. So we start in this manner, and this integral is easy enough to deal with if you just do basic substitution, aka u substitution, and the substitution should be like letting u equal negative x squared. Because I have a lot of videos on u substitution, I didn't think it was a good place here to show you how to do that. So basically, if you do u substitution and figure out that this integral is this here, then you can come back to where we left off, which is here, and say that the limit is a goes to infinity of 0 to a of this integral would just be same as the limit is a goes to infinity of, well, it would be this here evaluated at a and 0. And so when we evaluated a, we get negative e to the negative a squared. That's what you see here. And then minus, right, when we evaluate, we have to subtract. So minus, plugging in 0 into this. But when we go minus, this here is a negative quantity. It starts with a negative quantity, right? Like, or with a negative sign. So we get minus minus, therefore plus, and then it's e to the 0, because negative 0 squared is still 0, right? Okay, cool. And remember, e to the 0 is 1. So with that in mind, we see that what we have is the limit is a goes to infinity of 1 minus, right? So I wrote e to the 0 first as 1 over here. And then minus, the minus sign is from this negative in front of e right here. Yeah. Okay. And then I wrote this so that it has a positive exponent, which is 1 over e to the positive a squared, right? Like this. And now when we send a to infinity, we see that we're going to get 1 over something that tends towards infinity. So this quotient 1 over infinity, essentially, right? Like we'll go to 0. And so then we get 1 minus 0, or 1. Yeah? Okay, cool. So that's it for part A. And part B has a slightly trickier improper integral that we have to deal with. And that's this. Okay, cool. First, notice that we can take this negative sign and put it in front of the integral. So that's easy enough. And then what we'll have is like negative of the integral from 0 to 1, or negative the integral from 0 to 1 of ln of x dx. So basically, what I'm saying is all we have to worry about is like finding the integral of ln of x, and then taking the negative of it. Now, I already have a video where I show you how to use integration by parts to integrate the natural log of x, right? And so I'll link that video below this, but again, showing you how to do that in this video would not be a good call. So look at the video that I'll link to see why this result is true. That is why the integral of the natural log of x is x times ln of x minus x, but it is. And so then that means that when we take this negative and then put it in front of the integral, and then find the integral of this guy, then we like distribute that negative sign and we'll get this here. But at the same time, we need the grammar fix because we're dealing with an improper integral. And the grammar fix this time is, well, remember, the natural log is not defined at 0. So the way we get towards 0, as far as the natural log is concerned, is by going towards 0 from the positive x-axis, right? So going towards 0 from the positive x means that we have 0 plus, right? That's what this is showing. Okay, and then otherwise, we have changed the 0 to an a, and we're saying it's a goes to 0 from the positive side. All right. And otherwise, this integral that we actually know how to do right here, right? And the negative sign, as I said, will have instead of x ln of x minus x, it'll have us write x minus x ln of x, and that's what I have here. Otherwise, doing all of that, which is having taken care of the integral and then doing the grammar fix and then doing the grammar fix knowing that we have to go to 0 from the positive, we get this, and then, like, of course, because our integral comes with limits, we have to evaluate from a to 1, right? Okay, cool. So next is the evaluation piece. And so if we evaluate, then we plug in 1 first into x minus x times ln of x. And since ln of 1 is 0, we just get 1 out of that, which is when we evaluate 1 into x minus x ln of x, all we get is 1, and that's this 1 right here. Well, because this part, as I said, is 0 because ln of 1 is 0. And then when we do minus and then plug in a, what we're going to get is minus a, and then plus, because it's a minus in front of all of this with a plugged in, right? So we get minus a and then plus, and then it's going to be a ln of a, right? Okay, cool. And we simplify this a little bit more, and so we get this. And now when we send a to 0 from the right, like this a will turn into 0, but then we'll have limit as a goes to 0 from the right of this here, and that is going to be a little bit of work because if we, first of all, if we set aside this 1, right, and just concern ourselves with this limit here, well, as a goes to 0 from the right, we're going to get 0 times the natural log of a is going to go towards negative infinity. So we're going to get 0 times infinity, which is an indeterminate form of L'Hopital's rule, right? Like, or better yet, you could rewrite the a times ln of a as ln of a divided by 1 over a, and then you see that you get the infinity over infinity indeterminate form of L'Hopital's rule. And remember, while like there are many indeterminate forms that trigger L'Hopital's rule, you could really only apply L'Hopital's rule when you get to the infinity over infinity or 0 over 0 situation. And we have that here. We have the infinity over infinity situation. So we know that we could take the limit as a goes to 0 from the right of the derivative of the numerator divided by the derivative of the denominator, and that's what L'Hopital's rule says to do. So when we do that, and I already said long ago that we could use L'Hopital's rule, but yeah, when we do that, which is when we pick up from here, but then take the derivative of the numerator, which is that, and take the derivative of the denominator. Remember, the derivative of 1 over a is negative 1 over a squared, so that's this here. And then simplify here and evaluate, then good things will happen. In particular, when we simplify, we get just negative a out of this whole stacked up quotient on quotient, right? All right. And then, of course, when a goes to 0, we get 0. And so then coming back to where we left off, which is this here, we get 1 plus this we found out the hard way is 0. So it's just 1 plus 0, and therefore 0. Therefore, that's the answer we were seeking. And that concludes problem 2. All right, problem 3 to come, and I believe it's about convergence. And so check that out. And yeah, there are a total of 8 problems, and yeah, and they're all very different. So keep watching. Take care.